Hello, I am Nasir Ahmad, Assistant Professor of Physics, Government College for Chintamani. So in this video, you are going to study paper 503 of BSc Physics for 5th sem students under the topic Astrophysics, Solid State Physics and Semiconductor Physics. The contents of this video are Introduction to Superconductivity and experimental facts of superconductors like zero resistivity, persistent current, the critical field, the critical current density, and isotope effect. So the learning objectives of this video is to make students understand concepts such as superconductivity, critical temperature, zero resistivity, persistent current, critical field, critical current density. So the session outcomes of this video is that the students will be able to define superconductivity, explain the concept of zero resistance and persistent current, write an expression for the variation of critical field with temperature, explain the concept of critical current density, and the prerequisites for this video are variation of resistivity with the temperature in conductors and attenuation in conductors or materials. So what is a superconductor? So you know that we use electricity everywhere, like in our houses and streets, for lighting. Devices like television or computers, refrigerators, etc. also operate with the help of electric current. So electricity plays a very important role in our life. When we analyze the devices which operate on electricity, we find that some amount of electricity is always lost in the form of heat. So these devices are composed of vibrating positive ions and free electrons. So these vibrating positive ions offer resistance to the flow of free electrons in the form of collisions. This causes the loss of energy in the form of heat. So it is found that about 20% of electricity generated throughout the world is wasted due to the resistance of the wire and device. So we can save this much of energy if we can reduce the resistance of materials. In 1911, a Dutch physicist by name Kamerlingh Onnes showed that under certain conditions, some materials do not show any resistance. Such materials with zero resistance are called superconductors. So he observed that the electrical resistivity of pure mercury drops abruptly to zero at a temperature of 4.2 Kelvin, which is also called as the liquid helium temperature range. So continuous currents or persistent current flows for a very long period without any attenuation, which was named as superconductivity. Materials showing such phenomena are called superconductors. The temperature at which the resistivity becomes zero and material transforms from the normal conducting state to the superconducting state is called transition or critical temperature. So here is the graph wherein we see that we have resistivity along y-axis and temperature along the x-axis. So if the temperature is of a material is cooled from high temperature to low temperature, we see that suddenly at a temperature called as the critical temperature Tc, the resistivity of the material drops to zero. So below Tc the material will be in the superconducting state, and above Tc the material will behave as a normal conductor. So here are some examples of elements and alloys which show superconductivity at their critical temperatures. Okay, for example, vanadium has a critical temperature of 5.38, niobium 9.5, indium 3.4, Hg 4.15, lead 7.19. Similarly, some of the alloys have critical temperatures greater than the elemental superconductors. Like here, Nb3Ge has the highest critical temperature of 23.2 Kelvin. So some important observations are that all good conductors like copper, gold are not superconductors, and all good superconductors like zinc and lead are not good conductors. Non-magnetic impurity has no effect on the critical temperature value of superconductors, and magnetic impurity added drastically lowers the critical temperature of a superconductor. Sometimes application of pressure changes a normal conductor into a superconductor. The next topic is zero electrical resistivity. A superconductor is characterized by zero electrical resistivity. So it is not possible to test experimentally the zero value of resistance. So one method of knowing the sudden drop of resistance is to connect the material to a voltage source and measure the potential difference across its ends. When the material is in the normal conducting state, the voltage drop across the material is observed. When the material is cooled below its critical temperature, the potential difference or the voltage drop across the material becomes zero. So this tells us that the resistivity of a superconductor is always zero. Kemmerling Onnes devised a more sensitive method of ascertaining the zero electrical behavior of a superconductor. It consists of measuring the decrease of current in a closed ring of superconducting wire. When the superconducting ring is kept in the magnetic field and it is cooled below its critical temperature, it then becomes a superconductor. As we know, when the external magnetic field is switched off and induced current is set up in the ring, the decay of the current may be monitored by a change in the magnetic flux through a test coil held very close to the superconducting ring, inducing an EMF in the test coil. So careful measurements revealed that the resistivity of a superconductor can be assumed to be zero. Next topic is that of persistent currents. So when a current is initiated in a closed loop of a superconductor material, as shown in the previous slide, the current will continue to keep flowing of its own accord around the superconducting loop as long as the loop is held below its critical temperature. Such steady currents which flow with the same strength are called as persistent currents. It does not need any external power to maintain these currents, but there does not exist I square R losses. Calculation reveal that once the current flow is initiated, it persists for more than 10 to the power 5 years. The next topic is the effect of magnetic field. Superconductivity can be destroyed by applying magnetic field. The strength of the magnetic field required to destroy the superconductivity below the critical temperature is called critical field, Hc of T. If T is the temperature of the superconducting material, Tc is the critical temperature, Hc is the critical field, and H0 is the critical field at temperature 0 Kelvin, then they are related by Hc is equal to H0 into 1 minus T by Tc square. This is known as Tyen's law. By applying magnetic field greater than H0, the material can never become superconductor, whatever may be the low temperature. The critical field need not be external, but large currents flowing in a superconducting ring produce critical magnetic field and destroys superconductivity. So here in this graph we can see the variation of the critical magnetic field with temperature. So as long as the magnetic field is below H0 and the critical temperature is below Tc, the material stays in the superconducting state. For any values of H0 and Tc above H0 and Tc, the material becomes a normal conductor. And also we see here that as the value of H0 decreases, the value of Tc increases and vice versa. Next topic is the critical current density. When the current through a superconductor exceeds a certain critical value, superconducting property is destroyed. So current density corresponding to the critical magnetic field is called critical current density, and it is represented by Jc. So we know the magnetic field that is produced due to the passage of current through a wire of radius r is given by H is equal to I by 2 pi r. Hence we can write I equal to 2 pi r h, or IC is equal to 2 pi r hc. This is called as Shilsby rule. So critical current density is given by Jc is equal to 2hc divided by r. So here is a phase diagram. So critical temperature, critical magnetic field and critical current density are the three parameters that are going to decide the superconducting property. As long as the values of temperature, current density and critical magnetic field are below their critical values, the material will retain its superconducting state. If these values exceed their critical values, the material becomes a normal conductor. The last topic here is isotope effect. So we see that the transition temperature depends on the isotopic mass of the substance, and it is found that the transition temperature varies inversely as square root of the isotopic mass, or mathematically it can be written as Tc is proportional to 1 by m power half, or Tc into m power half is a constant. So the dependence of the critical temperature of a superconductor on its isotopic mass indicates the involvement of lattice vibrations in superconducting state. Thank you very much.